For introduction, this paper investigates the thermodynamic properties and performance of water-based nanosuspension in this application. Specifically, the study examined the internal and external irreversibilities within the refrigerant cycle when nanofluids are utilized, aiming to optimize the efficiency and effectiveness of heat exchangers. The motivation behind this research is rooted in the need for enhanced heat transfer capabilities in the refrigerant system, particularly as component miniaturization and compact heat transfer devices become more prevalent in modern technology. For basic principle, the refrigerant system operates based on this principle. The first one, refrigerant cycle. The refrigerant cycle is involve the process of evaporation, compression, condensation, and the last one, expansion. The second principle is coefficient of performance. The efficiency of a refrigerant cycle is often measured by its COP, defined as the ratio of the cooling effect produced to the work input required. Higher COP values indicate more efficient refrigerant system. The last principle is irreversibilities and entropy generation. Real refrigerant systems are not perfectly efficient due to the irreversibilities such as friction, non-ideal gas behavior, and heat losses. Reducing this problem through good design and material choice is key to making the system work better.
A very good day to my lecturer. My name is Naishwaran. The schematic diagram shown above represents a vapor compression refrigeration cycle with an internal heat exchanger, and I would like to explain about the diagram. First of all, the compressor on the point 2. The process on the compressor will be the low pressure, low temperature refrigerant vapor from the evaporator on point 6 enters the compressor. The compressor compresses the refrigerant, which increases its pressure and temperature. The high pressure, high temperature vapor exits the compressor and moves to the condenser through point 1. Next will be condenser. The process on the condenser will be the high pressure, high temperature vapor from the compressor enters the condenser. The coolant flows through the condenser coils, absorbing heat from the refrigerant. This process causes the refrigerant to condense into a high pressure liquid. The cooled liquid refrigerant exits the condenser through point 4. The next component will be internal heat exchanger, where the high pressure liquid refrigerant from the condenser on point 4 passes through the heat exchanger, where it exchanges heat with the low pressure vapor refrigerant coming from the evaporator. The process will be from point 5 to point 6. The next component will be expansion device. The high pressure subcooled liquid refrigerant from the heat exchanger on point 4 enters the expansion device. As the refrigerant passes through, its pressure drops and become a low pressure, low temperature mixture of liquid and vapor on point 5. This mixture then enters the evaporator. In the evaporator, the low pressure, low temperature refrigerant mixture from the expansion device enters the evaporator. It absorbs heat from the brine or the medium that being cooled, causing the refrigerant to evaporate into a low pressure vapor on point 6. The brine flows into the evaporator and exits after being cooled. This low pressure vapor then returns to the compressor and completing the refrigeration cycle. The main component process of the cycle will be compression, condensation, expansion, and lastly evaporation. And that's all from me. Thank you.
Hello, my name is Anik Lokman. Method of performance. Modern heat transfer device is already good, but there is still a limiting factor for it to function more properly, which is the poor heat transfer capacity of the conventional working fluid. We will further talk about the method in improving the conventional fluid by enhancing the working fluid with nanoparticles such as microparticles of metals like aluminium and copper, or metal oxide like copper to oxide and aluminium oxide. We will also discuss whether the nanoparticles enhanced fluid is better than the working fluid or no. First, we will talk about the Prandtl number. Whereas Prandtl number lower than 1 means it diffuses heat very quickly, while Prandtl number higher than 1 indicates low thermal diffusivity. As we can see from the graph, The fluid that was enhanced with certain amount of copper nanoparticles has a Prandtl number lower than 1, and fluid that was enhanced with aluminium oxide has a Prandtl number higher than 1. Next, this is the graph of entropy generated versus number of thermal units on the left hand side, and the entropy generated versus pumping power on the right hand side. From both of this graph, we can see that working fluid, which is water, has lower entropy generated, which means water will absorb the heat from the system much less efficient than the other two fluids. But note that it will require more pumping power since both of this enhanced fluid has a higher viscosity than the working fluid. But not least, we will discuss about the coefficient of performance of our system. As we can see from the graph provided, both of the enhanced fluid has a lower coefficient of performance than the working fluid for both refrigerant R22 and R200. As I mentioned earlier, this is because enhanced fluid has a higher fluid viscosity, which make it require more pumping power. This is the main reason why the doped fluid has a lower coefficient of performance.
Hello, my name is Arif. I would like to present the performance calculation system. The coefficient of performance, which is COP, of a refrigeration system is the main focus of the performance calculation. The efficiency of the refrigeration cycle is measured by the COP, which may be computed using a number of important factors. This is the Prandtl number formula. Prandtl number defined as the ratio of momentum diffusivity to thermal diffusivity. Prandtl number which is higher than 1, the momentum diffusivity dominates. Meanwhile, Prandtl number lower than 1 means the thermal diffusivity dominates. For example, liquid mercury has the Prandtl number lower than 1, which make the thermal diffusivity dominate, which deviate and make it diffuse heat very quickly. Another example is oil, which has the Prandtl number more than 1. This consequently makes the oil diffuse heat very slow. So this is the formula that is normally used to calculate coefficient of performance in the system. We also include each of the symbol and their definition. And here we are also provide an example and the solution on how to use the formula. There we have the data given. So for the solution, step 1, we need to calculate the temperature difference and enthalpy difference. Step 2, we calculate the pressure ratio and its term. And last step, we can get the final answer for the COP system.
Hello, my name is Tengku Imran, and today I would like to present the suggestion of system improvement. By using nanofluids, the refrigeration system can operate with lower condensing and higher evaporating temperatures, which helps in reducing internal irreversibilities. This improvement is attributed to the heat transfer enhancement characteristic of nanofluids, suggesting that they can still be beneficial if used to optimize overall system performance rather than focusing solely on the heat exchanges. Internal irreversibilities in a refrigeration cycle primarily arise from temperature and pressure differences in various components. By improving the transfer performance and adjusting the operating temperatures, nanofluids help in minimizing these temperature differences, thereby reducing the internal entropy generation. This results in a more efficient refrigeration cycle. Aligned with what I learned in class, reducing internal entropy generation generally makes a refrigeration cycle more efficient. Entropy generation is associated with irreversibilities in the system, such as friction, heat transfer losses, and pressure drops. These irreversibilities lead to energy losses, decreasing the overall efficiency of the refrigeration cycle. By minimizing internal entropy generation, the system operates closer to its ideal reversible cycle, thereby increasing the coefficient of performance and overall efficiency.